We are from Orobix. It's a company based in Bergamo that was founded some time ago. I'm the CTO. This is Lisa. She works with us since 4 years ago. So we hired her directly out of kindergarten. No, she was studying, and she's one of the key persons at Orobix. So what we do at Orobix is engineering system powered by AI, let's say deep learning, mainly. We focus on mission critical applications. So our goal is to go to production. So we're not focused on proof of concepts. For us, a project that has some degree of success in the project, where we can deliver AI in a real-world application, and we'll see several examples of that. We've been alive for a number of years. It's 10 years today. We haven't done AI all the time. At the beginning, we will see we're focused on medical image analysis using more traditional kind of algorithms. And since 2014, we're focusing on deep learning. We are ISO certified. In particular, we have a 13485 certification, which allows us to develop systems that can then become medical devices. So this is something that sometimes our clients ask. We're about 21 people. Oops. Oops. Right. Okay. Thank you. Okay. Better? We're about 21 people. We are here with booth, so we are growing, and please, you're welcome to come to our booth. All of us are graduates. 70% of us are engineers. We have about a half people specializing in informatics and mathematics. There are some PhDs, and about half of them are data scientists. So overall, we are 300%. And half of us are female, which is great. It's a very nice mixture. And on average, we're 30 years old. And considering that I wasn't removed as an outlier, so it means that we have young people like you. We are organized in 4 teams. One is a data science team that Lisa comes from. Then we have people devoted to applications. We see a number of them. And they are and another group caring about the infrastructure. And then there's an operation support structure that glues everything. Essentially, we were born in 2009. I was coming out of 10 years of research, and I really wanted to do something in the real world. And so my high school mate, Pedro, who was the co-founder, decided, him and I decided to start this adventure. As we had a business plan, plans for the future, a very narrow focus, and in fact we didn't have any of these. We just wanted to do something computer related. And so the first years we were just 2 people, 3 people, learning a lot of stuff. And I had been using Python since 2003-04. So that was a period of learning and growth. And at some point, we got the first contract in 2014 with a big pharma that gave us 4,000 scans, and we didn't know how to solve the problem that we were given. So that's when we first tried Torch, and we realized that people that didn't come from a medical imaging background could solve a very hard problem, segmentation problem. So we recognized that deep learning could have a real chance to make us grow. And so we spent a number of years, and we're still in that phase almost, doing engineering in which every project has some deep learning in it. And now we're starting a phase that we'll end this talk with, that essentially is a transformation phase from a purely project-based engineering company to a company that we know will exist in the future, which is the equivalent of an energy service company. An energy service company is a company that another company goes to manage all their energy infrastructure. So from the consumption, upgrades, and so on. So it's not a provider of energy. It's a company that the other company relies on to delegate the aspects related to energy. This doesn't mean that there's nobody understanding energy consumption and energy optimization within the company, but there is someone expert on the other end that provides the service at a higher level. So we want to do the same for AI and become an AI service company that the data scientists at the businesses that work with us can rely on and provide the infrastructure for. We work in life science, we do medical imaging, a lot of medical image analysis, analysis of clinical data. We work for pharma companies, device manufacturers. We work in manufacturing as well. We do a lot of image-based quality control and anomaly detection, some collaborative robotics. We call it everything else because, of course, the moment you decide to focus, you receive a phone call and say, yeah, there is this cool problem with Cherenkov telescopes. Do you want to work on it? Sure. You don't say, no, I'm focused on manufacturing that. Or you say, oh, of course. Same goes for gaming. And in gaming, you'll see something in the next slide. And also production planning. And we try to stay cross-sectional and just focus on the last mile of bringing advanced algorithms to production. As for gaming, we partnered with Milestone. We work with Milestone, which is a game developer in Italy, to develop or help them develop the first generation of purely reinforcement learning driven components in a game. And this is a game that will come out in June. So we're at the very last stages. This is what the agents see. You see a lot of trials, starting grades randomized over the course of the tracks. And this is the current gameplay situation where all the agents are controlled by a neural network, so there's no rule that drives the agents, but it's all self-play. So at the beginning, agents go randomly around the track or off the track most of the time, and then they learn to integrate the physics and to strategize and to manage the group behavior. So this is an example. I'm going a bit in some depth in this. This is an example of something we used Python heavily for. Each agent receives information about the location on the track, the nearby opponents, so how far they are somehow. So this is the Coca-Cola recipe in there, of course, what to show the opponents and how to reward them with a reward. We use a classical actor-critic architecture, and the agent controls the joystick every some tenth of milliseconds. And there is a LSTM module with some other stuff attached to it. That has to be very small because Nintendo Switch is a little bit more than a phone, or less than a phone, depending on your phone. And so other platforms have different constraints, but most of all, these kind of games are heavily graphics related, so you cannot occupy the GPU with it. So the network has to be really, really small. To train it, we partnered again with Milestone, and together we created this distributed training infrastructure in which multiple game instances with an ad hoc inference engine, because the layers are quite simple in the end, collect observations, actions that have been performed step by step, and rewards, shoot them into Redis, and then using Python we collect all the experiences for multiple opponents in a single game and from multiple games. We use PyTorch to backward differentiate, and then another PyTorch instance to collect all the gradients and update the network. And then export the network weights using the Onyx format back to Redis, and then the games can start again, and with an updated game. So with this distributed architecture, we can train a game from scratch in a matter of hours. So and the game itself runs at many times the real time, so that helps too. And having this kind of infrastructure using Python allowed the team to iterate very quickly to understand what were the observations, what was the reward that was needed to make the opponents play. For sure, this kind of work is not push-button work. It requires a lot of iterations. So the more infrastructure you can make, the better. You can check out, there's a video on YouTube in which, 10 minutes, we tell the story of how this project works. So we use Python across the board. We use it for deep learning with PyTorch. We use data science in general, the SciPy ecosystem, scikit-learn, scikit-image, and so on. We work with InMagic, which is a company based in Bergamo, and that develops the Django parts, a lot of Django applications for us. And we use it for microservices, integration with industrial cameras and so on, and medical imaging. So it's an essential component of what we do. Well, here you see some example of healthcare applications, and we go from, this is brain trauma, this is classification of lung tumors, this is segmentation of polycystic kidney disease, and this is going to be submitted to the FDA, so it will be a medical device submitted probably by the end of the year for a pharma company in the US. And the usual architecture when we go, for example, in hospitals, is to use open source software like Orthanc. Orthanc is a picture archiving and communication system that replicate and that can talk to institutional picture archiving systems in hospitals. And we do that to install an AI PACS in the institution so that radiological workstations can talk to it. And then we have our AI serving infrastructure that negotiates with that. And we use Redis heavily to manage queues and events. And in manufacturing, things are a bit different from the point of view of the task you have to solve. But in the end, the architectures are really simple. We use Docker, of course, a lot to develop all the microservices. We use Redis as a common blackboard or whiteboard where all the microservices can interact. And then we have to develop all the camera, PLC interfaces, ERP, and so on. We have done some open source work for segmentation. Maybe you can check it out. I don't want to steal too much time to this. This is a semi-supervised technique for segmentation so that you don't have to draw dense masks, but you can count two-point counting instead to perform image segmentation, keeping similar performances to dense masks. We have developed together with LAP, which is an institute in France, in the context of a project on Cherenkov arrays that have to detect gamma rays and discriminate them from protons, from gamma rays from deep space, an extension of convolutions to hexagonal grids. So you can now use all your convolution neural networks with hexagonal pixels, but actually they're a bit more general than that. So it's really been an amazing ride in these years. It didn't really look like that. It was more like something like that. Because unfortunately, things don't go always as expected, and almost never. And you have to try to actively make them go that way. And so we wanted to share a few lessons learned over the years. So now I described a bit what we do, but the core of the presentation is going to be this part. I hope we share suggestions if you want to embark in the journey of putting deep learning systems in production. And I would start from the typical, story you hear about how to perform a project. And this stems from being accustomed to, Kaggle competitions or blog posts. You get the data, you split, you train the model, validate, deploy, bye-bye. And this doesn't work, almost never, because this is good for a proof of concept, but there are a few complications. And I'd like to have Lisa talk about that a little bit on why this is where the project really starts and why it almost never happened that this was at the end of it.
Okay. Yeah, this is where we started. This is the process we usually did at the beginning of our project. And then we discovered that the problem usually is in the data. You cannot collect a big amount of data at the beginning of a project. Usually the things that work for us, it's more an iterative process, and it's what we do in our project now. So we tend to connect to the data generating process as soon as possible to collect all the real nature of the data. And we try to define KPIs at the beginning and to create an iterative process between us and our client to look at the data, improve the performances, and we want to do it iteratively because it really helps in deploy this kind of artificial intelligence process in deep learning projects, because we are not like usual standard techniques that our client uses until now.
Yeah, basically the way an algorithm behaves is really determined by the nature of the data. So in the end, this looks like an active learning paradigm, where you start from a V0, a V0, and then you have to identify, since you cannot collect 1 million samples of what you want, and maybe the 1 million samples only contain a very tiny amount of things that are interesting, so you have a very unbalanced data set. So you have to identify at every iteration what are the interesting data that you can use to enrich your data set. This sounds like obvious, but it's actually where the real pain is. And so how do you identify interesting data? And most of all, what process you have to establish at the client to make sure that this interesting data comes up? So we said, Lisa said that you have to connect to the data generating process. That's a key thing. The other thing is establishing some technique to identify the cases where the network doesn't perform well, where it fails. You can do it by manual inspection. So manufacturing line, something is discarded. You have to establish the process by which there is a human looking at what is discarded. It's painful, but if you don't do it, you fail. So you have to talk to your client and say, look, if you want to adopt this, do that. Put one person there for a number of weeks that is fixed, at looking at every thing that was good or bad. The lucky case is where there's already something in production, like a camera with a traditional software. It really speeds up things if you collect samples that were different, like in which your network thought that was good and the other thing was bad. Same thing in healthcare somehow. You can use uncertainty metrics, and we believe this is the way to go in the future, and we are developing some, we have some research and development in-house on this, using uncertainty metrics like keeping dropout on in your networks in inference to approximate how a Bayesian network would behave. Another thing is
stochastic weight averaging. There are a few techniques that allow you to put an error bar on top of your prediction. Usually these techniques do not work perfectly on the individual sample, but if your process, on average, in the last hour in production, had this kind of metric that was higher than normal, then possibly there's something new happening or there's something interesting that your network cannot really manage. And so that's where you want to collect your data. Same thing, but novelty detection and input is a similar thing, like novelty with respect to the training data. So you have to establish what the training data space was. So active learning, as this is called, is the key to reach the performance in mission critical context. So when you go to a client, you have to keep the phase where you're not in process as short as possible. If you're not in process, then you're in the POC time, and it feels great because the client thinks you're doing a great job. You think you're doing well, and you have your training, validation, but until you go in process, you're just doing preliminary work. So I'll tell you the sad story of rubber gaskets, which is we were called to solve the problem of identifying a number of defects in these gaskets which went high speed. And so there was the good ones and the bad ones. See a defect up there. And there were a lot of good ones. So if you stayed in production and collected good ones, you would have a big bag of good ones. If there are some bad ones in that big bag, it's not a big problem for a neural network. And so we had to pick bad ones. And so there were humans manually selecting the bad ones. And so they manually selected the bad ones, and then they acquired them, gave us the hard drives. We trained the system. It converts like in a very small number of epochs. And I was like, this is too good, but okay. We went to the client. We have the final solution, tried it, disaster. It was just like random. But if you really look at these two images, there's some difference. And the difference is these tiny white dots. This is dust that had accumulated because these pieces were manually selected. So they sit there for a while, accumulating dust, And so our network had learned to pick out the dust and say, this is a defect, okay? So this wouldn't have necessarily happened if we were in process. So not being in process means that you are a victim of biases that you cannot really predict. Don't be afraid of KPIs. So KPI, it's the same, it's connected to this. You have to establish KPI with your clients. It's painful, you don't know what KPIs are. The client will say, I want 100%. You have artificial intelligence, come on. You push a button, 100%. Of course you say, well, maybe yes, maybe not. So what do we do usually?
Yeah, usually we propose to our client to reach a base value. At the beginning, we asked the client to evaluate his actual performances, but usually the client don't know his actual performances. He said, oh, it's perfect. And so, okay. Well, with artificial intelligence, they said we should reach the 100%, but then we asked them to give us a base value which they retain acceptable to go in production. So we start acquire data and evaluate our performances, but usually are fine also if they are underneath the base value. And we try to go in production early because acquiring more data and retraining data allow us to reach the target value in not a lot of time on date. And our client usually is happy also without reaching the target value, because they can understand the really improvement of artificial intelligence is not the 100% performance, but that the errors and a deep learning system do are not so tragic like a traditional system, because it's more reasonable, like we said.
Yeah. It interpolates in between the training set values. So it's rarer that gross errors that come out from a traditional computer vision system, for example, when the computer vision system doesn't intercept a certain pattern. Usually the deep learning system gives you errors that are more in the gray zone compared to something that is grossly wrong. And since this system come up from experience, so they are trained from examples, you have to make the stakeholders, your clients, share the responsibility of their performance. So if they give you the data, here's the data, come back with a perfect algorithm, that's a recipe for disaster. You have to make them understand that the performance is connected to their effort in providing you the right examples. And that kind of solves the KPI monitoring problem. If you show them that by asking them to do some work, the performance has increased a bit, then they're hooked. They know that they can rely on their own knowledge to improve the system. And users will be happy to annotate, but you have to use their time budget wisely. That's why KPIs are so important, because they have to perceive that if they work 2 weeks or 1 month, they have an advantage. But of course, you have to create the tools, and we created a few tools. There's a tool called Dream that is an embedding visualizer plus annotation that really helps, that we connect with our infrastructure, so there's no give me the USB key, give me the hard drive, and I'll copy things over via FTP. Things are like streamlined and frictionless, and then they can provide feedback, classification, or for example, this is porosity in aluminum, segmentation that we can use directly then to iterate and retrain. I'm going faster here. You have to prefer networks that require less data, because you won't have a lot of data. Okay? Transfer learning sometimes helps, sometimes not. Usually we train from scratch. Since a number of years, we use architectures that help us control the training process. For example, prototypical neural networks are one of them. Instead of going out with a hard classification, this network output a position in a low-dimensional space that we can use then. It's like a glorified k-means. So that we can use them to assign, not only to assign a class to a sample, but also in inference to know where a sample is projected, and as we will see in a few slides, also to help clients define their own decision boundaries. So overall, this is a very good tool. It was created for few shots learning, but we use it all the time for classification problems. It's heavily, I won't go into the details, you can look at the slides, but or the paper. It's heavily randomized. It's not your usual training loop. You can take a look in our GitHub repository. We shared the implementation, and of course we changed it a little bit. This is an example of metal defects that we treated with this kind of network, and this is what you get. You get a good performance, like baseline performance, on less than 1,000 examples. In this case, this look easy, but they're actually not easy. Like, the client was enthusiastic seeing that, coming from the blob detection world, where it was really, really hard to detect porosity from dust. or damaged from dust because they're all dark blobs, and this kind of networks can tell them apart. And then by producing a low-dimensional space, we can also check, for example, if there's a case in which we should create another subclass. This is really important. Lisa does this all the time. Look at these spaces and decide that maybe here there's an opportunity to make a subclass, maybe elongated bumps. And then you can see the network kind of unraveling the sample or the training. And it's a really good sign that testing has a similar distribution. So now we know this is a good starting point because we know we are not overfitting too much. There's some confusion here. So we want to collect more samples of this. And this is a very practical way of also involving the client because clients understand it. So you have to make the training talk to you. So, for example, in this case, these are bushing, or whatever it means. I know the Italian word, but I don't know the meaning of the Italian word either, so it's kind of boccole, whatever. And they're automotive parts. And so this is what comes out of that. And so you can see, for example, that when you generate this low-dimensional space, you can also pick out situations in which there was a misclassification, or maybe this is the network not getting it right. But most of all, this gives you a perception of a few things. One thing is the network understanding what I want it to understand? We, as humans, reason by similarity. So if you ask me what kind of car I like, I will give you an example, but you will create an archetype of the car I like. And this is a way that non-expert users can interact. We have seen embeddings all the time. What I'm saying on blog posts and so on, Disney, and what I'm saying is that you should use them as much as possible to communicate results. Because you have to make inference talk to your users. And you can do that. For example, we did it in lung cancer staging for an application. This is lung cancer. This is large, but most of all, this is has some adhesion with the wall, and this is inside the lung. And this is a later stage, and this is earlier stage. But when you present, it doesn't have to be perfect, but you can present this kind of embedding to the doctor, and then for a new patient, present the 20 patients around that. And maybe among those 20 patients, 10 patients have nothing to do with it, and the doctor knows it. But the other 10 constitute new clinical experience that they can use. Or if you're in production, you see the production that in the morning was over there, and then it's moving down in the gray area more with a higher likelihood. And you can take actions, corrective actions, before you move to the failure zone. Of course, things are a bit idealized this way, but this is the kind of things you can do and communicate to your clients. And then you have to give stakeholders leverage on the results. So decision boundaries, you can move it. So you can have, so if they see that something is not quite right, you have to avoid that they feel that they have to go back to you for another training, because that takes time and it's unacceptable for them. So they have to have some leverage. Of course, they won't have full leverage, but some leverage on what the tiny decision, location of the decision boundary is. And we saw that this works, and we try to incorporate this in our software so they can shift the thresholds. Data is your source code. And so tomorrow I'll go in the Redis AI talk. I'll also talk about a software that a collaborator of Orobix in the context of a new spin-off we have. It's called TensorWork, developed, and the tool is called Hanger, and it's versioning for tensor data. Because you need if a client tells you, look, in this machine, I have, the client told me I sent him or her a faulted part 1 month ago, and the network was trained 3 months ago. You need to know what your data set was 3 months ago. And if you do this iteratively, it's really similar to versioning your source code. So you need to be able to trace and version your data throughout your iterative training process. And you have to focus on establishing processes at the clients. So you have to have your stakeholder involved, as we have seen, and rely on infrastructure, on technology to do that. Because if a business adopts AI for the first time, they don't have all these processes. They are not involved. They don't have those 10 minutes in which they look at the results, look at the data sets, and provide new feedback, and you have to establish those processes. And we're trying to put all this into a tool that we call Invariant, and we meant to release it earlier, but it's not released yet. We built it and dismantled it a couple of times, and hopefully this time is the right one. That basically is a conglomerate of all these processes where you have tools that we developed inside a containerized infrastructure, and there are already clients that have it. It can be on-prem or on the cloud, and it kind of it tries to remove all the friction from adopting these processes for AI. And it gives us the opportunity to become an AI service company that has oversight over all the application in a business or multiple businesses, using account people that can look at dashboards and prescribe that a network can be upgraded. So this is something that Lisa has done over the years, manually or semi-manually. So we're trying to take this and create a tool that allows us, and maybe others, to do this at scale. And so Orobix as a company can act as integrator or manager of AI processes and so on. So I hope this was interesting for you. You can hit us up at the booth. It's right beside the coffee table, so I think I will see you there. If you have questions, we'll be really happy to answer. Thank you.
Hi, congratulations for the talk and for setting up a company that succeeded in solving so many problems in so many fields. No? I have 3 questions.
Yep.
The first is this this cross-sectional approach is a benefit for you, or you just did it for survival? The second is deep learning is winning in each one of the fields that you are tackling. And the third one, how do you deal with clients which don't provide you labeling of data? What do you have a strategy for the painful task of labeling?
Yeah.
Thank you.
Okay. So I'll share the response with Lisa, but the first the first 2 questions were of course really good. The cross-sectional approach, we were on healthcare before at the beginning, like for first 4 years, when we saw that deep learning could allow us to take a step back and train a system to incorporate some prior knowledge without us knowing a lot about the process. And then, of course, in the engineering part, the application people have to have some specific engineering background when you have to talk to the PLC and so on. I think, in retrospect, I think it, no, because of course.
You did.
It was on purpose. So right now, we always resisted. We said, we have to focus, but in the end, we always resisted to it. And I think our ambition is to resist to it. And so in talking to potential funders, because we don't have any external funding, so we are looking for investors, of course, to kind of make the quantum leap to become larger. And some of them understand it, some of them don't, but we try to stick to it. Because in the end, we are focusing on something. And the processes that you have to enable are always the same. if you go to healthcare, manufacturing, or whatever else, they're always the same patterns, that we described today. And so Lisa has been involved in projects, healthcare, manufacturing. It's almost always the same process. And the last.
The second one is deep learning is winning in each one, the fields and the labeling.
Oh yeah. So deep learning is winning. I would say yeah. It
shall become a deep learning service company actually. This AI means.
Yeah, well, yeah, AI is easier to explain, but yeah, it's mostly software that learns from examples. So when you have software that is not pre-programmed, but learns from examples, then a lot of, like when you invite people at your wedding, right? You invite the cousins, then a lot of people come in, and if you extend it a little bit, you have a lot more people. So when you have software that learns from data, then a set of problems come into the room. And it's, you can solve them using a software engineering approach, but versioning data, having a kind of agile approach to, iterative approach to things. You can make parallels between traditional software engineering and not. But I think the kind of problems you have to solve are kind of always the same. And so it goes in pair to the cross-sectional part. So.
Yes, the core of our process are usually it's deep learning, and then maybe we use machine learning for post-processing or pre-processing to fix some aspect of the deep learning algorithm.
Yeah, and then we have a lot of engineering. So there are a lot of people, about half of them, that do the engineering part, which sometimes involves also top-down algorithms, mathematical modeling, and so on. And the last is labeling. I don't think it's our main problem, right?
Well, we usually insist with our clients.
Exactly.
Sometimes
she can be very
happens
convinced.
that we have to do it at the beginning, because even if it's not perfect, maybe our labeling in respect to a quality control team that do the labeling, our network are robust to the labeling type. Like if it's not perfect, the output of the network will be better than our previously segmentation, manually segmentation, for example. And then we ask the client to check the outcome of the first neural network we did. And it's more like iterative also. Or we check in the open source if we can use pre-trained neural network to start, to have a V0 and then start from it.
Yeah. Once you have a V0 and you can generate outputs, then the user is happier just not to start from a blank slate, but from something. But then they put in the time, because they come to us because they have a big problem. They cannot solve otherwise. Otherwise, they can go somewhere else. And so the problem hurts, and they are happy to provide their time in annotation. They're unhappy to do this, so we have to be very mindful of their time.
But when we started to see that
exactly.
it improves the performances, they really put some people working on it.
Yeah. So.
What's the question?
Well, thank you for the talk. Really nice. One very quick commentary question about using deep learning might be the thing that might be the case that you're winning with deep learning because of the kind of data you're using for training.
Yeah.
And the second, actually, my only question was if you can comment very quickly about. You said very, very well the problem of iterating over acquiring data, right? I was wondering if you ever tackled the problem of, once you get the data, you have to train test split, and you say that. But is it just one split, or especially on medical data? When you work on that kind of data, splitting the data in different ways might makes difference, and so
Absolutely.
the model might have different bias.
Oh yeah. Of course, it was very shallow slide. Yeah. There are all sorts of biases that are a lot more subtle than the dust grains I showed before. Yeah, so I totally agree with you. We don't always use deep learning. We use deep learning a lot because of the type of problems we are called into, and people come to us because we have these techniques. So we have some confirmation bias going on there. But in general, I think that, for example, for the application for the FDA, we also developed a similarity model for predicting if a patient is a fast progressor versus slow progressor, and we use random forest for that. But the processes were kind of always similar. Right? So I would say that we focus on software that learns from examples in general, and that can be it. And then test train split. It's very tricky. Right now, for that same project, we are writing the analytical validation and clinical validation protocols, and it's a nightmare because we have certain clinical trials data, they have certain selection criteria, but how is that telling everything about the population that we will apply on? So it's a can of worms. So those are the hard problems. If you notice, I didn't talk about choosing your favorite language or choosing your favorite deep learning framework or your orchestrator. I think if you are fine with what you have, you should go that way. Otherwise, you have more problems to solve on top. And sometimes, as a technical person, it's easier to focus on problems of technical nature than conceptual. So you really, really have to resist the temptation, and we didn't last year, to build something that forces you to spend energies in solving problems that you didn't have to start with. So that's the other recommendation to do. Use your tech savviness to your advantage in order to focus on conceptual problems like this one. That's last advice.
Thanks to Luca and Lisa.
Thank you.
Applause. And